Okay. Well, thank you very much, and good morning, everybody. I'm really happy to be involved in this nice workshop and to talk a bit about our control developments in the FLEXYNETS project. So I'm from the company Ensys, who is developing the control issues, which I will present now. Okay. So, sorry, I can't move the slides.
You should be able. Otherwise, you can use the arrows just behind your.
Okay, so I try to use this.
Okay.
Okay, no, it works. Okay, so Roberto mentioned already about the FLEXYNETS concept in general, so that we want to connect different sources and things in a low temperature or very low temperature network, which means that we have to integrate and interact and to implement an intelligent interaction and control of multiple consumers, prosumers and suppliers in a cold district heating network. Because we don't have a classical network in this stage as we had before, so we are faced with a problem that we have a transition in thermal networks, not only in the electricity grid but also in thermal networks in this case. So coming from the classical district heating system, this was one-dimensional with one heating source and a lot of consumers connected to a heating network. This is now also transferred to a kind of a prosumer network where we have not only one supply station but also consumers which are sometimes also acting as providers of heat or cold, and they are distributed within the network, which makes the control of the overall system much more complex at the end. So what is a problem? So we have one so here called a ring structure, and connected to this ring structure we have different storage possibilities. We have buildings which require heating energy for domestic hot water and for space heating, and they are typically connected to this low temperature heating network by heat pumps, which increase the temperature from the low temperature side to a higher temperature level, which is required for heating and hot water generation. We can also connect chillers or the waste heat from the chillers to such a network. So we are rejecting the heat from the chillers by using the thermal network. So here we feed in heat to the network, here we take out heat of the network. And there can be different sources connected, also waste heat from industry, solar thermal sources, which feed in at different points of the network. So this shows that there's quite of a complexity already within this thermal network, and balancing such a network needs some specific control features. And this becomes even more complex if you also consider the electricity network and the sector coupling between electricity and thermal energy, where we have at the generation side, when we have a cogeneration system, for example, which provides electricity and heat is fed into the network, and electricity is also produced, and we have the same case for other GHP units connected to such a network, or by the chillers also consume electricity, and by the heat pumps who consume electricity by providing heat. So there's an interaction between all these systems, and we can use this local flexibility in these different sectors, which are mainly provided by thermal storages, heat or cold storages, and by intelligent control we can control these systems in a way that we support the needs of the electricity grid. So when there's a lot of renewable energy in the grid, electricity grid, when we activate these systems and use electricity. When there's less renewable energy, then we live more or less from the storages on the different sides. So there's also this coupling to the electricity network. And we can also go further if you have THP units operated with a gas network. We have also a kind of an interaction with a gas network. So at the end we come up with a multi-level control optimization problem. So we have the local optimization in each of the single buildings connected to the heating networks. They need, of course, to provide the heat required to keep the temperatures at a certain level. And so to do this, there's a local optimization between the storages and the room temperatures. So this is a local system. Then they are connected to the network, and we have, of course, some heat supply because the different sources are not always equalizing the needs of demand. So we need also have some centralized sources which can be connected to equalize the demand and supply. And we have also some storages where we can store excess heat in the network. So this is the network balancing, so where we need to keep the network in an operational situation so that it always can provide what is needed at the different stations, substations. And if we integrate again the electricity network and the gas network, then we have another optimization level where we want to provide services to the electricity grid, or to use electricity when it's cheap, also gas when it's cheap. This is more or less the strategic optimization level which we need to address in such a complex system. Now, in FLEXYNETS we are developing control systems which are able to cope with this high complexity, and we subdivided the control in different levels. So we have the substation level, which you see down here, where we have the single controllers of the different devices in the single buildings, and also supply stations within or distributed over the network, and also the consumers or prosumers in the network. They are all locally controlled by controllers, which need to ensure that the needs are covered. We have also control of storages, which can be in the single buildings, or which could be distributed over the network or centralized. So they all need to be controlled by local controllers. So this is quite modular, and at the upper level we have a high-level system controller, which has mainly the task to balance the overall system, so that in order to always ensure that enough energy is available in the network. So this can be done also first on a local level, seeing what is happening in the network, and then reacting on temperature levels. But this can also happen on a more strategic level. So if I integrate, for example, electricity prices, gas prices, weather forecast data, so I know what my demand will be by predictions which can be implemented, and then I can develop a better strategy how the system could be operated in order to maximize, for example, renewable sources in this network, and this is all done in this management or strategic control level. From here, the high-level control gets operational schedules for each of the single devices in the network, and these are then transferred by the high-level control system to the single sub-devices, which then try to follow these schedules as long as possible. So how do we come to this optimized control? So we are using simulation tools, of course, on the first hand, to test on the one hand the control of the single substations, which are also quite complex if you have prosumer stations which provide heat and take heat from the network. So these are then built up in simulation models. We have models to demand, and then we have a control strategy which is implemented in these low-level controllers, and this can be tested in a simulation environment and optimized before it is really brought on site and installed. So this is an optimization of the more or less low-level control strategy. Then we have also some more advanced tools which we are going to use. This is a model-based predictive control, we have models of the buildings and of the systems installed, and we have control strategies which we are going to follow, or schedules for the operation of the different systems, and this can then be optimized in an optimization loop to find the best and optimum operation of the overall system. So this is quite simplified, shown here. It's rather complex in reality, but we are trying to cover some of these issues within our project as well. So how are we operating on the installation side or on the controller side? So we have, as I told before, we have substation controllers in each station, and this can cover also some sub-device controllers for the single devices within each substation. And this controller is then the master of these sub-devices of the station level, and is responsible to operate these systems in an optimized manner. And this is then connected also to a web interface where you can enter this controller and see what happens there, and also change schedules. And it's also connected to the higher level control. How is this control system structured? So the control code is more or less a C code in each controller. We operate with the same code. This code has different levels for different types of applications and systems integrated in the control of these systems. And we have an initialization file which then decides which components are really available at which controls substation, and then only these are activated and combined to a control system. So it's quite modular, so that we are really flexible in motivating on changing the different issues and adapting it to different possible substation situations. At the end we will have different substation controllers which are responsible to control the different substations and also the supply units within the network. And we are developing, this is also a kind of development work which we are doing now, to develop this high-level controller, which is the overall master of all the single sub-device controllers, and which is then responsible to balance all the network centrally. This can be, this is then connected to this supervisory strategic control, where these control strategies are developed using weather forecast data and modeling, simulation models of the tools, and from there we get the optimized control strategy, which is then supplied or transferred to the single devices. So this could be in future a cloud service or part of it, at least the strategic control level could be a cloud service, and we have one hardware somewhere in the network which takes the high-level control responsibility.
To conclude shortly.
I'm nearly through. So we have one demonstration site in Bolzano where we test all these control issues in a laboratory test system with a solar collector, gas boiler as heat sources. We have absorption chillers and ORC units within the system, and we have a network, simulated network here, where different substations, prosumer substations can be connected and controlled, so that we can really simulate a real network there. So this can have different operation modes from heating to cooling and distribution. So here you see some nice pictures of this demonstration site, which is out in Bolzano quite recently, and it's already in operation now, and we can now start in testing the different control strategies on a laboratory level.